Welcome to Breadboarding. In the previous video, we were looking at the various logic series that are available, and which ones we need to use for retro computing projects. So we covered the TTL, LS, ALS series. We also briefly mentioned the original CMOS CD4000 series, and also the HC and HCT modern CMOS versions. Now, I have been researching the Compact Despro 386 to do a 386 breadboard PC, and one of the things I have come across is the necessary requirement for using the F series or fast Schottky series. These are even faster than the ALS series, in fact, in some cases. Although it says up to 75 megahertz, the delays on these circuits for certain circuits is actually down to about 2 nanoseconds in some cases. So there are some timing sensitive aspects of the 386 project that are using sort of higher frequencies at 16 and 32 megahertz that may very well need these F series. So I've slightly modified my advice here in that I've now added the fast Schottky series here, which was originally introduced by Fairchild, and there's a number of these chips are actually used in the Despro 386 and also in the original PC-80 as well, I think. So I've just said here that the F series may be required for timing sensitive logic. And in this video we're going to be looking at the NOT gate, and we're going to be doing some experiments with the NOT gate to look at what voltages the various signal levels require and what happens when those voltages are not in range. This is video 7 in the How to Use Breadboards and Retro Digital Electronics series, and we're going to be looking at the NOT logic gate and the various chip families and what voltage levels those use. So in the previous video we introduced the logic gates, and in this video we're going to be looking at the inverter or the NOT gate. So this takes 0 input and outputs a 1, or inputs false, outputs true, or 0 volts and outputs 5 volts. And then in subsequent videos we're going to be taking a look at the AND gate, OR gate, XOR gate, and also buffers and what they do, particularly when we're looking at driving bus circuits and things like that, where perhaps there may be higher capacitance and resistance. And then the video after that we'll be looking at the inverted versions of these, and in fact there are one or two properties of the NAND and NOR gate, for example, that allows you to build all the other gates from these two gates, so we'll be looking at that. In the previous video we took a look at a nuts and bolts article, and we're going to be looking at some output from the second in that series. So we looked at the fundamentals part 1 in the previous video, and what we're going to be looking at is some of the information provided in part 2. In particular, there's discussion of all the various different TTL types, but there's also these tables and discussion of fan-in and fan-out. So I'm going to be basing some of this video on these tables, although I've annotated a little, so we'll go back to the slides to cover it. But I will include the link to this article in the description below. So in the previous video we covered the voltages that were required to signal whether or not something was a 1 or a 0, a true or false, and we covered the fact that the output voltage that the TTL series originally, so this is the standard in orange here, it would guarantee to output at least 2.4 volts, but it would recognise the high value as anything over 2 volts. So this gave us a noise margin of about 400 millivolts, 0.4 of a volt. And then from the output voltage for a low, then that would be a maximum of 0.4 volts, but it would recognise anything up to 0.8 volts as being low. And so that again gave us a noise margin for low voltage for, again, 400 millivolts or 0.4 of a volt. Now when we look at the other series that we've been talking about, so the LS and ALS series in particular, we can see that when we start to look across here, the propagation delay is how much delay is introduced to a signal that goes through a gate. So you'll see the standard TTL is about 9 nanoseconds. And you can see that for the LS series it's about 8 nanoseconds, so it's slightly faster than TTL, but the ALS is down to about 4 nanoseconds. Now, in fact, the F series, which is not actually included on this table here, but the F series is equivalent of about this AS here as well, about 2 nanoseconds as well. And then if you look at the power dissipation, this is how much power is used by each gate. You can see standard TTL is 10 milliwatts, LS is 2 milliwatts, and the ALS is 1 milliwatt. So the ALS series chips will use a tenth of the energy that the standard TTL does. The output level of standard TTL guarantees 2.4 volts, but LSTTL is 2.7, and in fact ALS is the supply voltage minus 2 volts, so that'd be about 3 volts. And that gives us a greater noise margin for the high signal, so 700 millivolts, 0.7 volts versus 0.4 volts here. However, when we get down to the low output level, you can see here that in fact we only guarantee 0.5 volts for these two chips rather than 0.4 volts. So in fact, in this particular case, in fact the new series have slightly less margin for noise at the low levels. And the reason why this is important is particularly if we've got long bus signals and things like that, then we have to be careful that we don't get stray interference actually causing logic levels to be misinterpreted. And in the Breadboard PC version 2, I ran into some problems to do with some of the reset high voltage lines that sometimes we picked up stray interference on the reset lines that were asserted when high, and so that caused some problems early on in the series. One of the other important aspects to consider with digital logic is the fan-in and fan-out. So how many inputs can be driven per output? Now in the original 7.4 TTL series, then in fact the fan-out and the fan-in was only 10. And in fact the parameters which are important for this is the output high current that it can provide was only 400 microamps. The input high required to an input was 40 microamps, so that would allow us to have up to 10 inputs driven by one output. And for the output current, the maximum there was, for low, that was 16 milliamps, and again each input required 1.6 milliamps, so we had a fan out for the low level for 10 as well. So the worst case fan out, we could only really guarantee that we could drive 10 TTL chips from the output of one TTL gate. Over here, this diagram I've augmented from the Nuts and Bolts magazine article, and what I've done here, I've added the LSTTL current levels on here. So once we've gone through here, we'll have a look at that. So the LSTTL, the output high current is the same as long with ALS, but the input current required for a high level is only 20 microamps for both of these. So this means that the fan out for the high level can be up to 20 gates. So we've got twice the fan out, so we can drive twice as many inputs from an output from this series of logic. If we were plugging one of these into one of the old ones, then obviously that would be reduced. But if we're dealing with all LS or ALS logic, then we can see that we can drive twice as many gates. When we look at the outputs current for the low level, then in fact it's half of what TTL can do. But because the input current requirement is about a quarter of that, and in fact in the case of ALS it's even less than that, then in fact we can actually have a fan out of 22 for the LS and 40 for the ALS. However, although the 40 here, this has caught me out in the past, although the low is 40, then the high is still only 20. So realistically, we should only be trying to drive 20 inputs from these chips. And what these diagrams show is what's actually happening, in that these things can be a bit confusing when you read them in the datasheet, but this is quite useful. So when we have a logic 1 input, then in fact at least 2.4 volts will actually be going through the input here to ground here, and it will be taking 40 microamps in the case of the standard TTL, and in the case of LS and ALS, it'll be 20 microamps. And then when we're doing a logic 0 input, then in fact what's happening will be 1.6 milliamps sunk effectively by the input. So effectively you've got to pull 1.6 milliamps through whatever we're connecting to this to actually signal the low voltage level, and that should be a maximum of 0.4 volts, and we should be able to sync 1.6 milliamps, or in the case of these other series, then obviously this is reduced at 0.36 milliamps, so we don't have to sync quite so much. So then when we're outputting values from TTL and in green with LSTTL, then in fact to output a high value, then in fact what we're able to provide is 400 microamps to a load at 2.4 volts as a minimum. And when we're outputting low level or 0 volts, then effectively what we're able to do is to sync up to 8 milliamps through a load here. So these values in the data sheet can be quite confusing, but I think this diagram helps to sort of show when you're thinking about these that in fact that outputting a low value actually is involving a lot more current than outputting a high value. So the main thing we have to worry about here is that the worst case fan out really is what we need to be thinking of. Although the ALS could do 40 for the low signals, it's not very useful if you couldn't signal the high signal. And also that the input low current that needs to be sunk is much less than the original TTL series. So what we're going to do now is to have a look at the data sheets for the basic inverter circuit. And this is just showing from the logic guide the SN74F series fast Schottky TTL. So I said 1978, I think this was introduced. And it's only through going through the compact Despro circuit diagrams, and there are a number of areas which are very timing specific that actually require these faster chips here. So this is the Texas Instruments hex inverter. So you'll see that there's quite a lot of different model numbers here. Now SN tends to be the part prefix for all of the standard TTL chips that we'll be using for Texas Instruments, and the 74LS04 actually tells us that it's a hex inverter in the LS series. But when we're looking at all of the information here, we need to be careful that we don't look at the basic 7.4 series, which is the original TTL, and the 5.4 series are in fact a sort of military spec parts. They're capable of running with more flexible voltage ranges and much higher and lower temperatures. Now when we look at the pin layout here, you can see that we've got the A inputs and the Y outputs, and we've got 6 inverters here, but this layout isn't actually particularly useful. And so, as we talked about previously, the chip labels that I either create myself or I reuse some of Grant Searle's chip labels. And if you look down here, you can see that the 7404 or LS, in our particular case, you can see with this chip labels, we actually see an outline of the logic symbol for the pins. So what I've done is I've cut some of these out and stuck them onto the chips that we're going to be using and we're going to be testing. Now in these particular data sheets, then I've chosen these particular ones rather than the very latest ones just because they have a little bit more information in. Generally, most data sheets will have some sort of function table that will tell us for the inputs and the outputs, the various highs and lows, what we would expect. And the inverter is about the simplest thing we can get. If we have a high input, we get a low output. A low input, we get a high output. This is the kind of the logical circuit diagram for it. So that's the inverter. So a little circle on the end generally means that the output is different from the input. And then these are the actual schematics of the internal circuitry within the chips. Now this first one here is the standard TTL one. Now we covered this in the previous video. It's very, very similar to the one we covered in the previous video. The only difference I think is that this is an additional diode here, and I think the value of this resistor was 120 ohms in the previous one, but pretty much it's the same. But then we've also got these other two here. Now the one we're interested in is the LS series here, and you can see here that it's quite a bit different from the one up here, and that we've got a lot of these funny shaped diodes here. Now these are actually Schottky diodes, and in fact these transistors here with this shape are actually Schottky transistors, and they will actually have a diode across 2 of the pins. And one of the things that this allows these transistors to do is they're able to switch faster, and they also use lower power. And in fact, when we were looking at the characteristics of transistors and we were talking about the TTL transistors being saturated, so they're full on or full off, well in fact with the Schottky diodes here, then these transistors are able to operate slightly outside of that sort of zone, and so they're able to switch a bit faster and use a bit less power. We're not going to go through the details of this, but you can still see there's the same sort of totem pole output, but this sort of Schottky circuit allows this to use a lot less power and to switch a bit faster. And the S series here, this was a faster series but a higher power, but we won't be looking into that. Now when we look through the data sheets, you'll see that these VIH, VIL, IOH, IOL, which we've already covered. Should generally all be the same for the particular series, but we do need to be careful that we choose the correct series. So this is for the basic TTL version, the original 7.4 series, and what we want to be looking at is the LS series here. You'll see the 5.4 series is in fact the military spec. But you can see here that again we've got a low level voltage, 0.8 volts, the high level output current, 400 microamps, the low level output current, 8 milliamps, and we can also see what the various other voltages are. So we know that with the LS TTL we'll get a minimum of 2.7 volts out for a high. Typically it says it's 3.4, and depending on the output current, if we're syncing 4 milliamps, then the voltage should be a maximum of 0.4 volts, and if it was slightly higher current, then we might actually sneak up to about 0.5 volts. So in general, if we're not sort of overloading the output of the chips, then we should be keeping to the 0.4 volts, but if it's obviously driving a lot, then it might sneak up a bit there. And then we can see here the typical sort of switching characteristics, so the number of nanoseconds it takes to actually switch from one value on A to the value out of here. And again, for the LS-TTL is normally fast enough for most of what we want, but we might occasionally need to dip into the ALS or even the F series if we need to get down to 2 to 4 nanoseconds, which in some particular circuits that could be important. And then we're into other series things here. Then these are just the test circuits. If we're actually doing the testing to try and verify the values that they have in the data sheets, then we'd really need to build these type of test circuits. Now, I'm not going to bother with doing the sort of detailed testing here. We're just going to stick these chips in a breadboard and we're going to just sort of see what the basic values and things we get off here. They're not going to completely match the spec values that we've got in this data sheet. So this is the breadboard we're going to be using. So this is basically the 74LS04 inverter chip, and it's got the chip label on. Got our USB power supply up here. Just got the simple LED here, blue LED, just to show when the power's on. What I've got down here is a variable resistor or potentiometer, and the inputs are connected to ground and 5 volts. At the moment, the input to one of the gates is set at 5 volts. I'll also do it at 0 volts, and then we'll put it into the middle there and we'll be able to vary the voltage that's going in. This other variable resistor here is a little more fiddly to adjust, but because it's got 10 turns on it, we can actually adjust that to be a lot more finer values. And what I've also done is I've actually put 2 resistors on the outputs of the first gate here. And these resistors have been sized such that we should be getting the current, so we'll have about 400 microamps for the high outputs and 8 milliamps for the low inputs. So I'll check those with this meter in a minute. At the moment I've just got 2 links here, but once we've started testing this, we will take those links out and we'll put in the ammeter and we'll just check to see what the values are on there. Just zoom in so we can see. Yeah, so you can see that the input to this is connected to our variable resistor here. Now at the moment it's just wired into 5 volts. I'll then do it to ground and then I'll put it in the middle there and we'll vary it. And you can see then that we've got this is a 10 kilo ohm resistor going to ground. So this is going to be syncing the current for the output high. And then this one here is 560 ohms. And this is going to 5 volts, so this is actually going to be syncing the 8 milliamps for when we're outputting a low. Then I've got 2 oscilloscope probes here, so I'll just switch over to the view with the oscilloscope. Okay, so we've got the oscilloscope here, so let's just turn it on first of all. So the input is the yellow one and the output is the blue one. And what you will just notice, if you see here, is that this thin blue line here is 0 volts, but in fact the output here at the moment, and when I read the value off the oscilloscope display, is about 0.34 volts. So the output low level isn't quite 0 volts here. So this is with the input tied to 5 volts. If we now switch it over to ground, be a bit of glitch when it switches over. When it settles down, you can now see that the input is now at 0 volts and the output is somewhere around, it says on display about 5.1 volts. So slightly above 5 volts in that particular case. So what we're going to do now is to just switch it over to the variable resistor. So I'm just going to turn it all around to one end. You can see that we've got the 5 volts is coming out there at the moment. And if I switch it quickly all the way around here, you can see that as we switch over, as it switches through around about 2 volts, it'll actually switch over to the high output signal. And in fact, if we just vary this quite carefully, when we get to about 2 volts, we'll see that in fact the 5 volt high value will just start to drop a little. You'll see there, when we're around about just over 2 volts, the output is still theoretically high, so it is over 2 volts. So, and the minimum output voltage should be 2.4 volts for TTL, although in actual fact for these particular gates, I think it's 2.7 volts. In fact, this value here is 3.2 volts. So it's actually come from the 5 volts down to about 3.2 volts as we approach sort of 2 to 2.2 volts. So now I'm just going to go a little bit up to about 2.1, 2.19, and as we just switch over 2.2 volts, then in fact the value switches down to 0. So in actual fact, you know, the datasheet said that we'd expect that it would treat a high signal, which will give us a 0 output, so the blue line should be close to 0. We'd expect that at 2 volts, but in fact, with this test, it only really switched over about 2.2 volts. So it is one of these sort of issues that if the voltages aren't quite sort of right, then you will start to get to see some sort of strange things occurring. And in fact, you can get situations, but particularly if you have any fluctuation on the power supply, where you may actually find that around a certain voltage with fluctuations on the power supply, you might even find that it will switch between high and low values around that sort of area. And if we then reduce our voltage lower, if you remember, we expect that low is anything below 8 volts, but in fact, because the output is high there, then in fact this is all being treated as low. In fact, now when it's down the bottom here, it's only about 20 millivolts above ground. So as we move this back up again, we're only guaranteed to go above 0.8 volts, will be treated as low. So we're about 0.8 there. But as we keep on going, then it's not going to get interpreted as a high signal until we get over about 2.2 volts. So up at 2 volts there, 2.1 volts, it kind of starts to change, but is still in the sort of zone where it's still counting as a high signal. And when we kick over into about 2.2 volts, it will then switch. So I think what we've been able to show here is that the values around this sort of grey zone can be a little bit flaky. And in fact, even in this particular case, that this particular chip is only really switching to the high value over about 2.2 volts. Okay, so that was the LS series chip. Now what I've got here as well, I've got a number of other chips. And one of the ones I was going to try is there's a CMOS HC chip that I'm just going to swap out. So we'll actually see what the different voltage levels for the HC series. So remember, this is the sort of CMOS series. So let's just swap that out. Okay, so that's in. Just power it on again. Let's just wind the input all the way down. So the yellow is the input. So when we have 5 volts going in, we have close to 0 volts coming out. I think it's about 0.3 of a volt coming out. Let's just switch it all the way to the other side to see when it switches over. So it's switched over there. So we've now got the output is 5 volts and the input is about 0.08 of a volt. But the interesting thing here is that it actually switched over at different points. So if we just increase this, let's see at what point this actually changes from being, so this is currently low. So it's kind of switching over. The output here is about 2.3 volts. This should be an HC series chip, and this should be about 3.5 volts. What I'm going to do is I'm going to disconnect these two resistors because I suspect it might be overloading the output of the CMOS chip, and just see whether or not that is any different when we try that. So we'd expect that the high value should be anything over about 3.5 volts and the low value anything below about 1.5 volts. Let's just try reducing this now from the 5 volts, see where it changes. So about 4 volts input there, 3.5 volts, 2.36 volts. It's starting to change there, about 2.1 volts, and it's flipped over at about 1.94 volts. So in fact, that one wasn't switching over at quite the same sort of range that I was expecting. So I might need to look into that. And I've got another one here, which is the HCT series. Now that should be the same as the TTL and the LS ones that we've been looking at. So let's just switch that out. In fact, this particular one's something called a Schmitt Trigger. And if we have a quick look at some diagrams to explain that. So a Schmitt Trigger has this sort of S symbol within it. And the key thing from the data sheets really is that you'll see this sort of symbol. So you see where this symbol comes from is in fact this sort of voltage curve here. What it indicates is that we've got a threshold voltage negative and a threshold voltage positive, and in fact that there's a gap between these two here. In fact, when we look at the data sheet, we'll see that the gap will be somewhere between about half a volt up to about 0.8 of a volt. And what this means is if we had a signal at about 1.2 volts and it was fluctuating around a bit, then it wouldn't actually switch because you'd have to have a much bigger variation in the signal to actually cause it to switch over. So Schmitt triggers are quite often used to clean up sort of messy input signals and things. And so what we're just going to do now is to see at what voltages the high and low values change for the Schmitt trigger. I'll just have a look at the data sheet as well. So this is in fact the LS series data sheet. The HCT should be almost the same just because it's supposed to be TTL compatible. And the key thing really here on the data sheet is that you'll see that this thing called hysteresis, so the gap between the threshold for the high and the low is a minimum of 0.4 volts, typically 0.8 volts, and could be actually more than that. So you'll see that the minimum value for switching should be about 1.5 volts, and the other way 0.6 volts, typical about 1.7 and 0.9. So we should be able to see that the output should actually remain stable depending on which way we're going for a larger period of time. Certainly as we're going upwards, then it won't switch from low to high until we get 1.7 volts, and when we're going downwards it won't switch from high to low until we get to 0.9 volts. So let's just switch this on. I'll just plug in the loading for this again. Right, so now if we try increasing this, so at the moment we've got a low input is yellow, and as it goes up, you'd expect to only see this jump up probably at about 1.5 volts there, and keeps on going up. Then when we come back down again, it should be it switched to about 1.5 volts. about 1.5 volts there, but it's not going to switch. It's switched now about 0.9 volts. So it means that there's this sort of 0.4 to 0.7 sort of volt range for Schmitt Trigger where it won't actually switch over. So the transition point between high to low and high has actually got a gap between it. So now I'm just going to switch back to the original chip we had, and we're just going to measure the currents. I'm just going to turn on the meter, put it in milliamps. So to start with, we'll replace this red link. So this is how much we will be sinking when the circuit is on low. So if we actually switch this over to low, and you can see now that the yellow input signal is high, the output is low, and you can see that in fact we've got about 8 milliamps being sunk for the low output there. So this is about a 560 ohm resistor. So work that out to give us about 8 milliamps there. So if we swap that out now and look at the other side, just take this one out of here and put the meter in here. Okay, so now when we switch our high input down to low, you can see what sort of current we get coming out. So this is the high output current that we're getting, and this is about 0.5 of a milliamp, so about 510 microamps. So it was rated for 400 microamps, so that's a little bit over it, but it's about that sort of thing. So we can see that there's a difference between the input and output currents between highs and lows, and that can be a bit confusing. And certainly when we're looking at the fan-in and fan-out figures in the data sheets, then in general, the main thing we need to be interested in is that the output low and input low, you divide one by the other, and that gives you your fan-in, fan-out sort of ratio. And if you do the same for the other, and if you're dealing with LS or ALS logic, then generally that's going to be 20. So I've seen the Schmitt trigger there with the different threshold voltages there. Now again, if we wanted to do that more precisely, we probably need to wire up all the extra components that the datasheet show that when they were measuring these, there were all various sort of diodes and all sorts of extra resistors and things like that. So we're not going to get exactly the same voltages that the datasheet gives us because we haven't actually measured it with that sort of circuit. One of the other things that we will be looking at in future videos is the buffer or the tri-state buffer. So a buffer normally just takes an input signal and outputs the same signal. So if you had a 1, it would output a 1, a 0 would output a 0. But a tri-state buffer allows us to effectively turn off the output and to turn it high impedance, or high Z as it's sometimes known. And what that basically means is if we've got, say, the computer data bus, for example, where we could have lots of different chips needing to talk to the CPU, for example. We might have the main system RAM, we might have ROMs with a BIOS, we might have all the other peripherals, I/O devices like floppy disk controllers, the video card, all those sorts of things. And these tri-state buffers basically allow us to effectively turn off the outputs for one particular set of devices, so that we only have one set of devices actually driving the buffer at any one time. So if we ever have a problem whilst doing projects where we're getting strange results, then sometimes it can mean if we don't have these control signals done correctly and we have two buffers actually trying to drive the bus at the same time, then that will obviously result in problems. So that's something that we'll be looking at in subsequent videos. And one of the other things we'll be looking at with the buffers is if we perhaps output a high frequency signal down different types of breadboard and stripboard, for example, then what happens to that signal at the other end, and how can we actually improve the signal and reduce interference on that by adding various sort of resistors and things, pull-up resistors to match the impedance on that. So during this video, we've been really looking at the voltages that the various chip series switch. So we've sort of seen that the output low voltage from the TTL was around about 0.3 volts. but when we were switching from low to high, it was actually occurring closer to 2.2 volts. Now, I'll put that down probably to the fact that we were not using the same measurement circuit that the datasheet had. But we can see that we were actually getting close to 5 volts coming out of there. But as we approached this sort of switchover point, then we saw that the output voltage came down quite a bit. So it was down to about 3 volts just before we started to switch. So you can begin to see that a lot of the time when you look at things, everything looks okay, but there are certain boundary conditions where things start to get a bit closer. And one of the problems I've had in earlier projects is one particular type of chip, so the 74LS646, which is the latch sort of buffer chip. It actually was having problems detecting low voltages. And in fact, what I had to do is to put a fairly low value pull down resistor, sort of between about 500 ohms and 1 kilo ohm, actually on the input so that they would actually get closer to 0 volts. So these things can really bite you. The only thing I was slightly surprised about is that when we were looking at the HC series, which is a CMOS one, then in fact it was actually switching from low to high at a much lower voltage. I would have expected it to be about 3.5 volts. Again, that could be down to the circuit that are actually using to measure it. And we've also seen that with the Schmitt trigger that we were looking at, so that was an HCT series Schmitt trigger, we could see that the low threshold here, as I think was about 0.95 volts, and the higher threshold here was about 1.5 volts. So by having these two different points here, if we have any fluctuation on the input signal, then it won't switch backwards and forwards all the time. It has to have a much sort of wider range of swinging voltage to actually cause the output to change. So that's covered the NOT logic gate and the various chip families that we're going to be looking at. And we've also had a look at the HC series as well, which we're not going to use very much of, although there is actually part of the Compact Desk Pro, the clock input circuit, that the Intel 8386 processor actually has a higher voltage requirement actually for the clock input signal. So in fact, we do actually need to use one HC series logic chip to actually feed the clock inputs of the 386. Now in the next video, what we're going to be doing is looking at these other logic gates and the buffer, so the tri-state buffer, and we're going to be playing around with the basic logic gates, but also seeing how we can drive sort of buses and what happens when we start to use higher frequency signals and what happens to our signals when we start to shove them down breadboards and down Veroboard bus rails. So that'll be coming in the next video. If you don't want to miss out on future videos, please hit subscribe. And if you can hit like as well, if you found the content interesting, it just helps to make the videos available to more people. Thanks for watching.